Hey, Vlad here, devinsidea.com. Welcome to another video. In the previous few videos, we have been stumbling on implicits left and right, and we even encountered type classes, which, at least according to me, are their most useful application. Now, I have promised you a video about all the nitty-gritty details of implicits for quite some time, and the time is finally here. Let's do this. All right, so far we have seen that implicits are tried in 3 different places, and it turns out that these are the only 3 places. Number 1, something wants an orange, but you're giving it an apple. Number 2, you're calling a method on orange that does not exist on orange. Number 3, you have a parameter list which is explicitly marked as implicit, which is also used to encode type classes. Now, we've seen examples of these in the previous videos, but I want this video to be self-contained, so we're gonna run through them real quick. As always, we're in the Ubuntu virtual machine and we're running Sublime Text, which is the editor of my choosing, which is fully maximized because I'm trying to save some space. And we're using a wonderful plugin called Terminus, which emulates the entire terminal, which runs SBT for us, which runs our main every time we save the file. So I already have a pretty simple project set up, so I'm just going to run through this so that you are fully aware what's going on. So we're using SBT 0.13.6, and our build file looks very simple. We're using only one compiler option, called -feature, and it's only useful because I already enabled it, because once we're going to start using implicits, we're going to get a warning saying, hey, use the feature flag, so that I will show you the actual warning. So I wanted to save you some time, so I already enabled it. And that is all. The other thing that we have is only the implicit main class, which extends app, which only runs hello world. So the first thing that we'll do is we're going to encode real quick this apple orange example that we had before. So I'm going to probably do that like somewhere in the middle. So as we've already seen, so I'm going to have a case class apple, which has a weight in grams like this, which is an integer, which has a color of string. And we have another case class called apple. Orange, we already have an apple, right? It also has the weight in grams, weight in grams like this, which is an integer, okay? And we're going to have a function that wants an orange, but we're going to try to give it an apple. Okay, so the only thing that it will do is it will have this print line over here, right? It will have it twice, okay, like this, and all it will do is it will print out the orange. And maybe I can scroll down a little bit here, and we don't actually need that. We also don't need the sidebar. Okay, so this is all that we have so far. Now we're going to have an implicit def apple can be used as orange. And by the way, if you haven't seen the previous videos, no worries. I'm gonna make it self-contained. I'm gonna run through this real slow once I finish typing it. Okay, so we have the orange apple dot weight in grams. Okay, so this is just a function that takes an apple, produces an orange, and it is marked implicit, which is why it will be used during the implicit resolution, which we're gonna talk about way too much today. Okay, so we're gonna call a function. And obviously we can't just give it an apple, but we will still try, okay, like this. So we're going to have weight in grams equals 300, and the color is going to be red, like this. So the only reason why this is going to compile and run now is because this implicit keyword is there. And now we already seen the warnings. We're saying, hey, this is the proper warning, which says, hey, use the language implicit conversions over there. Maybe we should actually go and put it in right away. Let's go back to the build file. Put it over here, okay, as a string like this, close, go back, come on, go back here, reload, run it again. All right, so now it works again, but this time without warnings. And in fact, maybe I don't need these print lines over here. It looks kind of silly now. Okay, let's remove that. Okay, so if this method has not been marked as implicit, then this thing would not work, and we would be forced to do it manually, right? Apple can be used as orange. We're wrapping this apple like that. So we're doing this basically manually, okay? And I don't have scalar reform enabled, so I have to inline everything myself. All right, so the method apple can be used as orange is known as an implicit conversion, or as I prefer to call it, it's an implicit because it's very sneaky. You don't really see that it's being applied, right? So if I comment it in like this, right, you don't see that, right? So you're passing an apple to a function that wants an orange, and somehow magically the conversion is happening. So implicit conversions like this are being frowned upon, and this is also why we see the warnings. Now, implicits are a very powerful and useful feature. So they're not intrinsically evil. It's just that with these conversions, and in particular with the implicits, you just have to be able to always hardcore justify their usage, right? But as I said, they're not intrinsically evil. There are very, very useful use cases for them. Remember in the homegrown collection series, for example, we used it to work around issues with variants, or for example, in the Scala standard library in the Predef object, there are methods that implement the type widening. For example, every time you have a function that wants a long, but you give it an integer, the implicit conversion kicks in and does that for you. So they're not intrinsically evil. However, it will be also super simple to create a conversion that takes a long and converts it down to an integer, and therefore it will cut off some pieces of that integer. So it will be very, very dangerous because it's very, very sneaky, right? So when they're applied, you don't really see them, right? So all of a sudden you're going to be wondering why you lost some money. So the next one is actually called the explicit implicit, right? Or it is also a kind of implicit conversion, right? So there are two implicit conversions. There are implicit implicits and explicit implicits, and they also go by the name of extension methods. So if we have it over here, we have an implicit def called apple wrapper, which takes in an apple, right? And instead of producing an orange directly, it produces an apple wrapper. Right? So this is just a helper function to create an instance of an apple wrapper, right, like this, which is going to be just a final class apple wrapper. Over here, it takes in an apple, right, and what it does have is a method called toOrange over here, right, and the implementation is exactly the same as at the top. So if I duplicate this line and I go down over here, right, so the implementation is very, very similar. It's just that the usage is a bit different. So I'm going to copy that function call over here, right, and I'm gonna paste that in over here. So this is gonna be an apple, oh my god, what did I just do? Apple wrapper like this. And what we can do now is we can go over here and call toOrange as if it has been defined on an apple, right? But it's not. So this is why it's called an extension method. We're basically extending the apple with the method called toOrange, right? So what was happening behind the scenes is that an apple is being converted into an apple wrapper, like this, okay, and we're calling toOrange actually on that, right? So it's exactly the same thing. So I'm going to comment this out, and I'm going to comment this out. And by the way, it's not a convention to call these implicit conversions with a capital camel case, right? But basically, this is exactly why I am doing this, because I wanna have the same name as for the case classes, because there's actually an even better syntax for them, which I'm going to show you in just a few seconds. One last thing to notice about them is that, well, it's not really the last thing. It's just that extension methods are a pattern that is used in many languages these days. It's a very modern feature. It's just that in Scala, because because implicits are used for them, they're a bit more powerful, because there is actually an implicit conversion is happening, so the type is changing, right? So all of a sudden, this is not an apple anymore. This is an apple wrapper instead, right? So it's not just the fact that an apple has this method now all of a sudden. Also, the type is different. Now, the reason why I called this function apple wrapper with a capital camel case is that if we remove that, we can use a better syntax if we use an implicit keyword over here, right? Implicit. And I think I prefer to have it over here. So it's a final implicit class, okay, like this. Okay, let's remove that. Okay, so it's going to do exactly the same thing. In fact, what is being generated behind the scenes is exactly the same code. So it's actually called apple wrapper. And we will discuss it by the end of the video, that the names for the implicit conversions usually don't matter, but there are a few cases where they actually do matter. Okay, let me revert that again, like this. Now, this syntax over here is called a syntactic sugar, and because it's called a syntactic sugar, because it is a syntactic sugar, it naturally comes with limitations. For example, exactly for this one, you need exactly one parameter. So for example, if you use implicit derivation, where you have implicit derivation is essentially where you have the implicit keyword twice in the same line. This is a bit of a vague explanation, but essentially you have an implicit conversion which also wants an implicit parameter, right? So for example, if we mark this as an implicit, then the compiler should bark at us saying that implicit classes must accept exactly one primary constructor parameter, right? And in this case, what is happening is that sometimes it's 0. All right, so it is also common to have this val as a private val, and it is also common to call it self instead of Apple, and also it's very common to extend any val just so that the instantiation of the objects is being avoided, right? So you have better performance and better memory consumption. And the last thing that is common is to call them Apple ops, as in operations on apples, okay? And therefore, this thing is actually called now Apple ops as well. Apple ops like this, but again, it doesn't really matter how it's called behind the scenes. Okay, so yeah, so this is the final version of this syntactic sugar for extension methods. It just is one thing that you need to be aware of them is that remember that they're generating this def over here, right? This one, which is called Apple ops. Okay, and this means that you actually can't, even though it's a class, you can't put this class outside of an object, right? Usually you would be able to put a class in there, right, like this, but because it generates a def cannot live on its own outside, okay, outside of objects. So it is very common to put them into package objects, but there's this thing called the excellent -excellent compiler flag, which will warn you about some suspicious usages and so on, and it will bark at you if you actually put this implicit class into a package object, because it will tell you that you should not put classes into a package object. You should put classes into their own respective files, and therefore what you should do is you should create a class, a regular class, put it into its own file, and then in the package object define this implicit conversion, and we're going to talk about this a bit more by the end of the video. All right, so explicit implicits or extension methods are generally very user-friendly, so they're not being frowned upon as much as implicit implicits. In fact, they're used to create very, very powerful DSLs. In fact, libraries like, for example, Scala test would not be possible without them. Or the fact that, for example, you can call an arrow on anything, and this will be used as a factory to create a tuple. In fact, let me show this to you. So this is in the standard library. There is this implicit final class called arrow association. It's not called arrow ops, it's called arrow association, and it takes a private val self, which can be of any type. It extends any val, and it defines this method called arrow, where you can pass it some b, right? So you had an a, you pass in some b, it creates a tuple 2, right, just by using self and y, and also it uses another def with a Unicode character for the arrow. In fact, you know what? There's also a compiler flag that I'm going to go to the build file and I'm going to enable it. It's called no predef, right? So if you go over here and say -y, it's a capital Y, no -predef, then what will happen is that in our files, like usually in every file we have implicitly, automatically, we have this predef object imported. Right, but what will happen now is that it's not imported, and let's see what happens. Okay, first of all, it doesn't find println because println is defined in predef. It just delegates to console.out, the standard out println. Also, look at this value star is not a member of string, right? So what is happening here is that the strings are being converted to some string wrapper, and this string wrapper has the method called star, multiplication, which accepts an integer and so on, and produces a string. All right, now let me revert that real quick. So I just said that the explicit implicits, they allow for powerful DSLs, and they're generally very, very useful and very user-friendly. However, they can also be used to create harmful situations. Again, this whole topic about implicits is, it's a very, very powerful feature, so it can be abused like crazy. Okay, so the next one that I'm going to show you, it is also in Predef, defined over here. It's called any to string add. So what it does is it adds the plus method to absolutely anything, and it just concatenates string. So examples like what I'm going to show you next are happening all the time. Let me go back to my VM. Let me go back to over here, right? So I'm going to go down over here. So what you can do is you can println a 1, which is a string, right? And you can call plus with a colon on a sequence with a 2 and a 3. And if you have missed my video about this, then the only methods that end with a colon, they're actually right associative, which means that they're being called on a sequence, right? So this code is exactly the same code as calling over here dot plus equals and passing 1 as the argument, right? So this is exactly the same code over there, right? So it just prepends the 1 to the sequence of 2 and 3. The problem is that on the string, there's also a method called plus, which is concatenation of strings. So now this is what is being created. Now there are no implicits involved so far, right? It's just a regular string, and it has a method called plus, and as a parameter you can pass in anything that you like. The problem appears when you do it the other way around. So if you try to print out the sequence of 2, comma 3, like this, okay, and you try to append a 4, right? So this is a different one, right? So this is a colon plus, so it doesn't end with a colon, therefore it's left associative, right? So we append a 4, right? And if you make a mistake, if you're a beginner, or maybe if you're an experienced programmer who's just, I don't know, tired or something, right? If you forget this colon, then an implicit will kick in. It will convert this sequence into what was it? Into this class, which is called lowercase, right? Called any2string add, and all of a sudden you will have a plus function there that you can pass in a string as a parameter, and all of a sudden it will do concatenation again. So basically what I'm showing you is that even extension methods can be used for relatively harmful things, and we will also learn by the end of the video how to unimport a few implicits. Generally prefer to use string interpolation for string concatenation. All right, so we got implicits, and we have extension methods or explicit implicits. And the last place where the implicits are tried is in the implicit parameter as implicit parameters, but it actually should be called an implicit parameter list or implicit section. So we're going to have a method called method, and it will take an A, and it will have another parameter list, right? So function curring is happening, and we're going to have an implicit parameter list, right? So it's very important. It's not just an implicit parameter; it's an entire parameter list with 2 implicitly requested parameters over here, B and C, and the whole thing is producing an integer and just adds them all together, right? A plus B plus C, right? We could actually call it plus. I'm going to keep calling it method. So what we can do is we can print out method with a 1, and as a second parameter list, we're going to pass it an 2 and a 3. In fact, maybe actually go and do that. Right, so we just see our 6. Maybe let's duplicate that, go down over there. Okay, let's have it maybe over here, like that, okay, and let's duplicate it again like that, put it over here. So now it's going to look a little bit more beautiful. Okay, so now if you have a stable identifier somewhere, right? So if you have an implicit val or an implicit object, we're going to have an implicit val over here, which is called whatever. The name doesn't really matter, and it's an integer, and it's a 4. Then now all of a sudden you can call this method like that without specifying the entire parameter list, like this. Okay, so it's exactly the same code. 1, 2, 3. I mean, exactly the same code as if we were using the 4 over here, right? So this is doing exactly the same thing. 9, 9. Okay. In fact, maybe I'm going to do that. Okay. Now we're going to get to the part of the video which explains all the rules surrounding the implicits, but at least over here already I will tell you that, first of all, the implicit parameter section has to be the last one, and also you can have only one of them. So I'm going to show it to you by having an implicit x over here, which is an int. So if I'm going to try to compile this, it's going to say exactly what I just said. An implicit parameter section must be last, and multiple implicit parameter sections are not allowed. So let me revert that so that everything compiles again. Now the next thing that you need to understand is that the entire implicit parameter list must be specified, right? So if I go over here, if I remove one of those 4s, it's not going to work. And also at this stage, I should also warn you that you probably shouldn't mix default parameters with implicits, right? So if I go over here and I do 4, then all of a sudden it will work. But let's see what happens if I'm going to use a 5. So over here, it actually used the 5 and the 4 and the 1. All right, so we're not going to go into details about this, so about like mixing default parameters and implicit parameters. Okay, so now if I did everything correctly, then at least by this time in the video, you should come up with one question: what happens if you have multiple implicits defined? Let's try that. So let's say that we didn't have just whatever; we had also whatever 2, and it was a 5, for example. Okay. Now, what is happening here is that basically the compiler barks at you and says that implicit resolution requires a unique instance for the type of type to be in scope, and for that reason, it is advised to not have irregular types or common types as implicit parameters. So what you should do instead is you should create 2 very, very specific case classes, right? So you're going to go to case class over here, call it first, right? It's going to have the value, which is an integer, and we're going to have second over here. right? Come on, second over here, right? So we're gonna say, okay, this is not an integer. This is, in fact, you know what? Let's create another one. Let's create a method 2 over here, right? And we're gonna say, okay, this is not an integer. This is the first, and this is a second. By the way, let's remove the 5 over here. I don't like it. Default parameters. Okay. So now the implementation would be a plus b get the value out plus c get the value out. Okay, let's fix all the errors that we have laying around. Okay, so first of all, you can't do only one. Okay, what else? Yeah, we have two implicits over here, right? So now we can go and say, okay, so this one is the first and this one is the second. So we're just gonna wrap this 4 into first, right? Like that. And we're gonna wrap this 5 into second, like that. All right, and now it should be fine. Gonna find implicit value for parameter b. Okay, which line is it? 60. 60 is over here. Right, so at this point we should try to call the second one because we don't have those implicit ints laying in scope around anymore. Okay, so what did it say? Oh yeah, so over here it's the same thing as wrapping this one, and let's make it a 5. Wrapping this one into a second 5. Okay, now because these types are so specific, what did I do again? This one, the print line also needs a parenthesis. Okay, right. So because these types are specific, you will not run into the situation where you have ambiguous implicits. Now the same thing also applies to implicit conversions, and also it applies to the topic called type class cohesion, which we'll talk about a little bit later in the video. Now, if you wanted to see if there's an implicit instance for something in scope, we could write a method that does exactly that. We're going to call it getIt, right? And we'll take some parameter, which is it. Like that. Okay, so it's basically the identity function returns it again like that. Okay, so this is essentially the identity function, and if we have a different version of it like this one, which has this one marked as implicit, okay, let me comment this one out, then we can just see if stuff is laying around in scope. For example, we can say print out get it, and we can call it first. Right, so we're saying, hey, is there an implicit parameter for this type class? And if there is, then the compiler will put it over here, and this method will return it, and we will print it out. Okay, so there is one for first. Okay, it looks like this, and this one is already defined in the Predef, which is imported in every file, and it's called implicitly. So we actually don't need it. We can use implicitly. It looks exactly like that. It is laying around somewhere in the Predef. Okay, so if it's not there, right, so we can do, for example, implicitly for char, then the compiler will tell us, hey, it's not there. Could not find implicit value for parameter e. Character. It says a parameter e because implicitly is it's just a def, and it has a parameter, and it's called e. Okay, let me remove that. Note that contrary to the popular belief, it also works with add expansions. For example, we have a def over here that can take an apple and produce an orange. So if we ask the compiler to show this to us, right, so we can say print line implicitly a function that takes an apple and produces an orange, then it will actually find it, right? So it will go to the method, it will add expansion is going to kick in, it will convert it into a function object, and the implicitly will find it. At this point, we should probably talk about the most amazing feature of implicits is that their resolution is happening at compile time. So it's not going to explode into a user's face, which is an amazing thing to have. Now, there are some caveats to this, but for the most part, it pretty much works as expected. Now, the compile time thing is a curse and a blessing because remember, a compiler is a simple program, right? It takes .scala file as inputs and it produces .scala files as outputs. And therefore, even though for you as a user there is some magic involved, but behind the scenes, the compiler is cooking with regular water, right? So it's a regular application, and therefore it will cost you some compilation time. Do not forget that. So overuse of implicits, or simply saying actually the use of implicits, will always cost you the compilation time. This is one of the reasons why people are always complaining that the Scala compiler is too slow. It's not. It's just doing a bunch of things. Also, I cannot stress this enough. A compiler is just a simple program, so it might contain bugs. It might produce unexpected behavior. I'm not a compiler guy myself, but it looks like a very complicated feature to create or even to maintain. So yeah, it's a very powerful feature. So with great power comes great responsibility. And I actually promised myself not to say this, but now it slipped out. We'll talk a bit about type classes a bit later in the video, but I sort of want to finish the syntax part of the video, so we're going to do type classes real quick. And also I want to show you like one of the typical issues that arises with implicits. So we're going to have a trait called SomeType class for type t, okay? If you have never seen type classes before, watch my previous video, or basically follow along over here, is basically, so this is a type class for some type t, it has a method, some method which wants one of those t's. And then you go and you have an algorithm which is defined for the t, right? It wants some t, it doesn't know anything about the t, but it wants an implicit instance called some type class for type t, produces a unit, right? All that it's doing is printing out instance dot method. I call it some method, right? And it gives it that t over here, right? Okay, so defining the instances of the type classes looks like this. So you can have an implicit object, and you define in an instance for strings, for example, extends some type blah 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 for string, and whoops, I pressed a P. I wanted actually curly braces over here. So if it has a some method over here for the string, returns an integer. We're going to ignore the parameter here because this is not the point over here, right? So now we have all of that stuff, and now we can use the algorithm, right? We can use the algorithm by giving it a string, whatever, and it's not going to work for example, for a character, right? For example, or for a number, right? So if you go and do this for the number, it's not going to work because there's no instance for an integer, right? So it says couldn't find implicit value for parameter, instance for integer over here. So this is why it's called type classes, right? So this is a type class. This is an instance which is required over here. The compiler injects it because it's an implicit parameter list. Okay, so there's a better syntax for that. So if you're gonna have an algorithm 2, it's defined for t, and now you have a context bound over here, some type class for type. Notice that there is no t over here, right? So it's just like that. Okay, so it gets in the t and it produces a unit, and it's doing exactly the same thing, right? So it's doing the same print line, but the instance is not in scope anymore, right? So we have to retrieve it, and how are we doing it? With the implicit function, right? So we're saying, hey, give us that that type class. Okay, it's still not going to work for ints, okay? But what it will do is it will work for the algorithm too, right? So it's just another syntax for exactly the same thing, okay? These two are absolutely equivalent. Now check this out. We already have an instance for strings. Check it out. What is going to happen if we use an implicit val, and we define another instance for strings, right? I'm going to call it lowercase instance for strings, right? So it's exactly the same thing essentially, right? So we're going to have some type class for, I'm sorry, that should be a colon, obviously, right? So it does exactly the same thing for strings, okay? Equals, and we're going to use anonymous classes over here. So we're going to have some class for string, subtype class for type string, okay, over here, some method t string comes in, integer, and we're going to use a 10 over here. And let's see what happens. Now, what you probably should have expected is that because we have two instances, the compiler should bark at us and say, hey, there are two instances. But my hunch is that the compiler is resolving, right? The implicit resolution is finding this instance because it is more specific, right? So because this one is essentially of type like this, dot type to some class of type string, and this one is from string to some type class of string, right? So this one is more specific, and I believe that this is why the compiler resolves it. But honestly, at this point, your hunch is as good as mine. We're going to comment this one out real quick. And the next thing that we're going to do is we're going to talk about view bounds that are very similar. They're not related to type classes, but they're very, very similar to this syntax. So I'm just going to show it to you. And in fact, this syntax is going to be deprecated pretty soon. So we're going to have a algorithm 3 defined for t, right? It gets in the t, and now it wants an implicit convert t to int, okay, and produces a unit, same thing as before. So it does print line convert t, okay. So let's go over here and do the algorithm 3. Now this obviously requires that we have an instance, right? So we have an if we have an implicit def, I'm gonna call it c, I'm gonna call it conversion. I don't know why. Okay, so it takes in a string and produces an int, and it just returns something. Doesn't really matter. I just wanted to compile. So we're not going to call it because we don't have this conversion. In fact, maybe we could call it with an integer, right? So if we have an algorithm 3, we can call it with 1, 2, 3. That come on, 1, 2, 3. That should probably work. Yeah, because it's already an integer. Okay, so another syntax for that would be very similar to the context bound. In fact, let me try to have all of them in one viewport, so to say. So if I'm going to have def algorithm 4, And now it's going to have t, and this is called a view bound, and it's going to be deprecated very, very soon. So it wants a t, right? So from this point on, it looks very, very similar to type classes. So it wants to do print line convert t, but convert is not in scope anymore. So it's going to convert implicitly, okay, and it's getting out, using the edit expansion, this thing. So it's exactly the same thing. Algorithm 4, there we go, right? Exactly the same thing. So this is, I just wanted to show you this, these context bounds, which is over here. Right, this is a context bound and this view bound, and the view bounds are being deprecated. The fact that I said already like 100 times in this video and in the previous videos as well. All right, so let's talk about the rules for implicit resolution, which means the rules that the compiler is taking to resolve your implicits. And there are quite a few of them, and some of them are pretty nasty, but the first two are very, very straightforward. Okay, so the first one is called the explicits first rule. So if your code compiles without any implicits, then no conversions are going to happen, right? Even though they're in scope or something, they're just not going to happen. Okay, the second rule is called the marking rule. So only the things that are marked as implicit will be resolved, right? So if I remove this implicit, for example, over here, all of a sudden some code is not going to compile because it's just not going to be used during the implicit resolution. The third one is the one that we have already seen, this non-ambiguity rule, right? So you can't have like two of the same instance laying around. For example, if I go over here and look what's going to happen. So if I have this implicit val over here, I'm going to copy that, and I'm going to have another one. I'm going to call it like 2 over here, and this one is going to be it's going to be 30. So even though if we don't have this object over here, these two will actually bark on each other and say, hey, ambiguous implicit values, right? So they're really the same. And by the way, when you're dealing with implicit instances, use implicit vals. Favor implicit vals to implicit objects. Even though it requires a bit more syntax, implicit objects have quite a few bugs surrounding them. So prefer implicit vals. Okay, so let me remove one of those instances like this. Okay, it compiles again. Actually, I'm gonna go back a little bit because I forgot to mention one thing. So if you have 2 of them, notice that they compile perfectly fine until you start using them, right? So if you don't have the usage code in there, you can absolutely have both of them floating in the same scope, totally fine. Only when you start using them, only then it's not gonna work. Okay, let me remove it again like this, and it should compile now again. Okay, everything's cool. The next rule is called one at a time rule. Okay, so if we go to the top where we have the implicit def, orange can be used, apple can be used as orange. If I comment it out, then some code is not going to compile. Okay, so if we go over here and we define 2 of them, right? So we're going to like jump through an integer. Okay, so we have apple to int first. It takes an apple, right, like this, and it produces an integer somehow, right, by just getting the weight in grams out of it. Okay, and we have another one. We have an implicit def int to orange. Okay, like this. Some int comes in, and finally the orange comes out. And what it's doing, it creates an orange by giving it the integer, right? So this code still doesn't compile, even though like technically everything is necessary, everything that is necessary to make the conversion, right? So for example, over here, instead of this line, we could, for example, we could take the apple to int, and we can give it the apple, okay? And then we can take this entire thing and also give it to the other one, to int to orange, right? So this is exactly the same code. So now it's actually going to work, right? Because this implicit is back in scope. But if it wasn't in scope, it wouldn't work, right? Because it applies only one implicit at a time. Now there is a workaround for this called implicit derivation, and this is what I'm going to show you now. So if you comment this one in and we comment this one out, and we're going to go over here and we're going to say, okay, there will be another parameter list, right? Implicit convert, right? So this is basically the view bound from apple to an integer. Then all of a sudden this should work, I believe. Well, we commented out this one. Okay, so we need to do it ourselves. So we need to create the orange ourselves by converting an apple to an int first. Okay, like that. The next 2 rules are a bit more complicated, and they can be presented one at a time because they're actually very intertwined. One is called the naming rule, and the other one is called the scoping rule. To demonstrate the naming rule, which basically says that names don't matter, this basically is a factory for oranges, right? So why can't we call it just orange, right? Can we call it orange? Yeah, we can call it orange. It's fine. Now, the only exception to this rule is when you want to import, for example, one implicit but not the other. This would be the time where you actually need to know the name of the implicit conversion. And the scoping rule goes in and says, okay, an inserted implicit conversion must be in scope as a single identifier, right? Or it might be associated with the target or the type of the conversion, right? Or the type of the object. We're going to talk about this a bit later. Okay, so basically it says that it has to be in scope as one identifier. However, check this out. First of all, let's revert this to a simpler conversion like this, right? So let's just do that. Let's remove these. All right, so it basically says that if you put this thing into an object, right, then all of a sudden it's not going to be found because of the scoping rule, because it's, first of all, it's not in scope as a single identifier. But secondly, look, if I import it, right, import blah, everything in blah, then all of a sudden it still doesn't work. Even if I import it like this, right, it still doesn't work. So there are some corner cases in which the name actually matters. So it's actually confused because it's called exactly as the factory for the orange, right? So if I call it however I want, right, and I just import blah, then all of a sudden again it will work. So this might actually be a bug in the compiler. As I said, it's a very, very big, very complicated, nasty feature. So there are plenty of bugs, plenty of unexpected behavior, things that should work but they don't, and the other way around as well. Now, there's another part that I prepared for you that I'm going to skip because I don't want this video to get way too long again, as they always do. But basically, the issue is with the naming rule is the accidental shadowing. For example, in the Predef object, there is a method called, the one that we have seen over here. In fact, it's not this one. It's this one. It's called augment string, right? So string comes in, string ops comes out. There's also another one called wrap string, and wrapped string comes out. Now, if you define an implicit conversion in your code and you just happen to call it like that, then it will shadow this one and your conversion will apply. And, this will surprise probably some of your users or some of your colleagues, okay? And also, this is very much related to jar-hal, which is an issue with class loaders that load wrong classes, right? Because over here, this is an implicit def, but if you had an implicit class, then you would also need to fight that. You'd also need to make sure that all of a sudden, the name of the class is not shadowed, and the class itself is being properly loaded, right? So I wanted to show you this, but I'm going to skip this part just to save some time. Let's go back to my virtual machine. One last thing that I forgot to mention is that what I usually do is when I have implicits in my library, I append a suffix to them, right? So I say, okay, this is an implicit from my library, right? So if I have a library called hell, it's going to be an implicit from hell. All right, so the last part of the implicit resolution is basically the scoping rule, right? So there's a fixed path that the compiler traverses to try to find your implicit instances, right, or your implicit parameters. And the rules behind this are very complicated. And in fact, I copy-pasted them from a wonderful book called Functional Programming for Models. It's a very pragmatic book by Sam Halliday, and I really, really liked it. So this is basically the list. So basically, as a rule of thumb, the closer the implicits are to your code, the more likely are these ones that are going to be taken, okay? So the first one is a normal variable scope. It is search for implicits in order, right? So the first one, you have the local scope, then you have the outer scope, then you have the ancestors, right? So the classes that are being extended. Then you will have the package objects, and then you will have the ancestor package objects, and then you will have the files imports. And if all of that fails, it will try to go to the given parameter type, the expected parameter type, and the type parameter. It will go into the campaign objects. And this is what I meant a little bit before when I said, that the implicit conversion must be defined either in the surrounding scope, or it must be defined on the source, on the companion object of the source, or on the companion object of the target. So what we're going to try to do is we're going to try to reproduce this whole thing. So what I'm going to do is I'm going to go and I'm going to remove basically everything, even the print lines, because we basically just care about compilation. So what I will do is I will also make sure that the incremental compiler is not gonna ruin anything for us. So we're gonna go and do clean every time, and we're gonna do compile every time. Okay. In fact, you know what? Let's do running. Let's do running. Running is fine. Okay, like this. So we're gonna have our apple and orange again, but this time they're gonna look a bit differently. So we're gonna have just a message, which is a string over here, and and we're going to have another one called orange over here. It also takes the message, takes in a string, okay, and we're using the message just to override the toString method. Final override def toString, which is a string, right? Just produces the message over here, and let's see if it compiles. Yep, it's all good. In fact, we could even have them outside of this object implicits like this. Let's have them outside. Okay, so now over here inside of the object, we're going to have my print lines, which probably shouldn't have removed, to 500 like this times 50. Let's have them twice. Let's print them out because I want to see them and I want to be able to copy them like that. Right, I shouldn't have removed them before. Okay, so in between, we're going to have a very close implicit, right? So we're going to have an implicit def apple to orange 1, right? So I'm calling it 1 because I'm basically saying, okay, this is the first one that is going to be found. And sometimes you can have sort of multiple of them, and the code is still going to compile, right? So if they're not in the same scope, but they're like on the path, like different ones of them on the path, sometimes you can have multiple of them, but sometimes not. Okay, so we're going to have an orange, and it's going to pass in 1 as the message. So this is going to become the toString. Okay, so now over here, we're going to have an orange that is actually an apple with a message of whatever. This one is going to kick in, convert the apple into an orange, and now we're going to print out the orange like this. Okay, so this one is equivalent to an implicit conversion that is defined in some other class, right, in some other object. So if we had an object over here and we have, I'm going to call it imports, and we're going to put the same conversion in there, then if we comment this one out and we imports like this, then it's still going to work exactly the same way. And I'm saying it that they're on the same level and they're using, you know, the same number 1, because if we if you bring them to the same scope, then it's going to be ambiguous, right? Let's go up. Yeah, type is match. That is so weird. It doesn't even warn you that they're ambiguous. Maybe if we have this import over here, right? No, still not. Maybe if you give it a different name, let's call it apple to orange x like that. Yeah, so what happened right now is actually this thing that I didn't show you. It actually happened, this name shadowing, it kicked us in the butt. Okay, so what is happening over here now is that the names are different. If as soon as they're in the same scope, I believe it doesn't matter if you import it first or not, then you have both of them and they are ambiguous. So what we're going to do is we're not going to use the imports anywhere. Okay, so just because otherwise it's going to get like way too confusing. Okay, the next thing that we're going to do is we're going to put this thing into its own scope like this. It's going to start over here and it's going to end over here. Okay, we're going to do that. And what we're going to do is we're going to take this one, copy it, and paste it over here like that, and call it 2 over here. Let's see what's going to happen. All right, same thing, ambiguous, blah, blah, blah. But if we remove this one, then it still will be found, right? So it goes local scope, then the outer scope, and so on and so on and so on. The next one is the ancestor. So if we have over here a trait, I'm going to call it ancestor, okay, over here. And I'm going to take one of these, put them over here, and I'm going to say that there's a 3. There's a 3. Okay, so what's going to happen is that we're going to extend the ancestor over here, and then it's going to go into local scope, then into outer scope, and then it's going to go into the ancestor, or with ancestor, obviously, because we already have extends app. And as you can see, this one can coexist with this one, right? Whereas this one, maybe this one can't. Let's see. Yeah, this one can't though. It's really it's really weird. It's really like, imagine teaching this to beginners, right? Like, how the hell can a person remember all of this? It's crazy. The next one is going to be package objects. So if we're going to go over here, we're going to create a file here, and we're going to call it package.scala. Okay, we're going to create a package object implicits over here. Implicits, okay, so I'm going to call it a 3.5, okay, because it's sort of on the same level as the ancestor, right? So if we bring it over here, I'm going to call it a 3.5, and I'm going to use those backticks over here. Okay, let's do a 3.5. So now all of a sudden it shouldn't be able to coexist. Oh, it actually does coexist. Oh, it coexists because I copied the trait. I don't need the trait over here, right? So let's do that, right? So now it should, yeah, so this is exactly what I wanted. So it's basically on the same level as the ancestor. Sort of almost, because it can't actually coexist with this one, but it still will be applied eventually, right? So the 3.5, okay? The last place where it's going to look is the companion objects for the apple and orange, right? So we can go over here. We can say, okay, this is an object apple, okay? And we're going to take one of these conversions, for example, this one. I'm going to put it over here, right? And I'm going to say that this is the sort of the fourth place. Right, so notice we're not importing the apple, right? But it's still going to use the 4 if we don't have that implicit conversion in the package object. Let's do that. Okay, so it's taking the 4, and the same thing would happen with the orange. In fact, they would be ambiguous if it's defined in both of them. Orange. Okay, so I'm also going to call it 4, right? So it's going to work with an apple or with an orange, but not with both. All right, that's basically it. I have a few extras to add, so I'm going to remove the package object, and I'm going to revert everything in that file until we have our big example. Like before, I started, doing that. Go back, because I need some code from there, and I don't want to start typing all of it again. Okay, remove that. Come on, go away. All right, so this is the code that we had before. Maybe it compiles, maybe it doesn't. Okay, it actually does compile. Okay, so over here, we have the instance for the string, which is coming from here. And if we did not have the instance for the string, then this is what the compiler would say. It would say, hey, could not find implicit value for parameter instance. Okay, what you can do is you can go to your type class, which is over here, right? And you can add an annotation to it, right? Scala.annotation. Implicit not found, right? And you can say over here, give me an instance of some type class for type for $, and you can use T over here like this, right? So the error message is going to change now because we have this annotation over there, right? So it says, give me an instance of some type class for type for string. The compiler inserted the string over there, right? So one thing to remember is that this annotation goes onto the type class, right? Not onto the instances or not onto the algorithm. It can only be used on the type class itself. Now, let me actually inlines instance because I wanted to compile. Okay. Next thing that I want to mention is a compiler flag called xprint typer, which I'm not going to show you because we already have like a way too big example. But essentially, it will show you what the compiler compiled your code to, so you will see exactly which implicit instance is being used, which is really cool. But I'm not going to show it to you. The next thing is that sometimes, especially when implicit derivation is involved, and if you have also implicit classes defined in companion objects, then the compile time can increase dramatically. For example, at my work, we had a clean compile of a project would last for like 7 minutes, and then I would add one implicit to one of the very top package objects, and it did what it was supposed to do, but the compile time basically skyrocketed. It went from 7 minutes to almost like double, to almost like 13 minutes, which was insane. Right, so always pay attention to compile times and pay attention to putting implicits into your companion objects, and be very careful with implicit derivation, especially with very nested types. All right, as I already mentioned, sometimes harmful implicits can be disabled by simply unimporting them, and there's another way to sort of disable them is by adding an implicit conversion yourself, and then this ambiguity thing will kick in, and the code is essentially not going to compile. So effectively, you're disabling this harmful implicit. And there are a few actually SBT plugins or compiler plugins that use that, and one of them is called WartRemover, and I'm going to make a video about this probably at some point. Another thing is that you should always annotate the types for your implicit conversions. Okay, so for example, over here, maybe I don't need to do this. Let's see. Right, so the compiler inferred that type, but it's still very advised to always annotate them. And in fact, in Scala 3, it might not be possible anymore to leave them out. Now, I didn't really want to mention this, but there's a very important topic for type classes called type class cohesion. Now, in Haskell, where this feature is coming from, type classes are a bit more limited. So the places where you can define instances are very limited. You can either define them in the same place where the type class itself is defined, or at the same place where the thing that you're defining the instance for is defined. Now, you can also define orphan instances anywhere you want in the program, but this is very much discouraged, and you get warning. warnings. Now, by doing that, Haskell basically ensures a bit more sanity, right? So there's like a little bit hygiene around type classes, and this hygiene is called type class cohesion, right? So cohesion basically means, you know, to bring them as close as possible together to make them, you know, one thing. Okay, so informally, like I watched a very cool YouTube video that I'm going to link down in the description, and there was like a list of what cohesion means informally, and I sort of stole it again. So it means that for a given type class, for a given type, there is 0 or 1 instance at all times. No matter how you ask for an instance, you get the same one. And if an instance exists, you can't not get it. Right, which I found super useful, and this means that at least in Haskell, type class cohesion, even though it's not like completely enforced, but at least it encourages. It doesn't encourage. It basically prohibits a usage of custom local instances, as I have shown you. You know, there's this passive implicit, so you can have multiple type class instances, which, you know, wasn't really designed, you know, for type class from the beginning. And also you can have, like, you know, multiple of them, right? So yeah, so you shouldn't be able to have custom local instances, and you shouldn't be able to have multiple instances. I'm actually going to show you this real quick. So because compared to Haskell, type classes in Scala are pretty much a Wild West. So I'm going to remove everything over here. I'm going to create another object, main extends app extends app, like this. Okay, and if we print out a list of 2, 1, 5, 4, 3, then we can call sorted, and what sorted wants is it wants an instance of the so-called ordering, which is defined somewhere in the Scala standard library. Now it turns out that we can't just define a local instance, which should not be possible with, you know, according to type class cohesion, right? We can go here and say, okay, ordering of ints, right, equals, and there are multiple ways to create an ordering. I'm going to use the this one, reverse, right? So now all of a sudden, because this thing is in scope, the list is reversed, you know, it's sorted in reverse. Now it seems super useful, right? Very useful, but it should be, it should be better to use it explicitly, right? Like this instead of implicitly, okay? Because this violates type class cohesion. This thing could live somewhere far away, be brought in by some import or by some ancestor that you don't even see, and all of a sudden your list is sorted in the other way. Now, there are many details about implicits, so this video would just keep going for hours and hours and hours. I obviously can't list all of them. For example, there is a plugin called simulacrum, which actually generates type classes for you, not instances, the actual type classes. I'm going to leave the link down in the description. Then there is this thing called generalized type constraints, which we're going to talk about, about them in some other time. Then there is also the fact that type classes don't play well with irregular subtype polymorphism, right? Because there are different kinds of ad hoc polymorphism, type classes and subtype polymorphism, right? So I'm going to create videos about them, individually, because this video has already gotten way too long, as freaking always. So the last two things that I'm going to say about them is that first, in some cases, the IntelliJ IDEA can actually highlight implicits for you, and secondly, implicits are a very hairy feature, and for many reasons, they're being entirely revamped in Scala 3. So if you're watching this video by 2020 or maybe 21, then some of the things that I showed you today might not apply anymore, but I'm sure that by that time I'm also going to have a video about them in Scala 3. Alright, I gotta admit this video was not the most fun to make because it's basically just a never-ending list of rules and freaking exceptions and whatnot, which is probably also one of the reasons why I delayed it for so long. But it's done now, so without any further ado, it's been Vlad, devinside.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.